So we have first a convolutional layer, and then we will talk about filter, and then we will talk about pooling, of which there are two types. There's average pooling and max pooling. So suppose we have, and here I'm going to write some math from this book. This, by the way, I know I promised to share the list of books, but let me just point this out now because I have it here. This is one of the best written books on machine learning and especially neural networks. Is this one. Muhammad Zaki, Data Mining and Machine Learning. I mean, this book is just pleasant to read. The book gradually built on basic concepts and works its way up. I highly recommend you get this book, either in physical form or digital form. So let me show you the way that they use the notation here for convolution. We'll begin with a one-dimensional convolution, and then we can extend that idea to a two-dimensional matrix. So suppose we have two vectors. I'm going to slightly adapt the writings here. Now, a picture is a matrix, but let's begin with one-dimensional first, with the components, x sub 1, x sub 2, etc., etc. And we have a filter matrix. Excuse me. We're talking about the vectors. This is one-dimensional for now. So in one dimension, convolution. Now this book uses W because while we are convolving it with a filter vector or a filter matrix, the components of a filter vector or filter matrix are really weights. So it makes sense. I will also use the same convention. We will make this W, and it will be weights. Now, what you need to know is that the number of components or the dimension of the weight and features are not the same. And here's, I'll write down the mathematical notation, but then I'll show it to you pictorially. It's a very simple concept. Now, we denote a convolution with an asterisk. So we take our two vectors, x and w. We will perform an element-wise operation on the components of both vectors. So we have x sub k, I, and then I think this is o dot. And so this dot inside the circle is the element-wise operation. What we are going to do is we will take, let's say, now x sub k refers to a section of the vector. Let me show it to you here. And it's okay for me to show you this page because the author actually made the slides, many parts of this page available online for free. I'll try to find the link. I think if we Google Zaki, the website will show up. So I look up the slides. The slides are quite helpful. I mean, the author did a tremendous job of explaining these concepts pictorially. Yeah, so this is the cover of the book. Now let me jump to that section. There we go. So this is our vector, yes? This is what I mean by sub section of the vector. So if your filter is 1/3 vector, what you are going to do is do an element-wise multiplication. So 1 times 1, 3 times 0, 1 times -2. And then the sum of that. Same thing here. 3 times 1, 2 times 2. So 3 times 1 is 3, 2 times 2 is 4. Obviously, the 0 cancels this other one out, so you get 7. Now, if you notice here, there's a fourth term, the term stride. A stride is how many, strides you're taking in the vector. Like how many strides, imagine this is your vector, this is your vector, how many strides are you going? Like how many components are you skipping? I mean, it's pretty clear in this picture. Here, the stride is 1. So initially the window, if the filter was multiplying this first 3 components, and then we take a 1 stride down, and then we do an element-wise operation. And then we continue this way until we've covered the entire vector. This is the product or the result of this convolution operation. And this is what that notation is representing when I say x, for example, x sub 1, x sub 2, x sub 3. Okay? So x sub 3 is the number of components you're multiplying. This corresponds, the subscript corresponds to the size of the filter, here denoted by W. So the first subsection, the second subsection, third subsection, and you are going to add the result of this element-wise operation. That's what you're seeing here. So this sum is that value. This sum is that value, and so on. And then you will sum up all of these together. So you're going to add up -1, 7, 5, 4, -1. And this will be put into another matrix. So if I can scroll down here, let me jump to and show you the 2D version. So this is 2D convolution right here. There we go. Same idea. This is applicable to what we are doing. Okay. Again, even in this example, we're going in strides of 1. So multiply element-wise, right? The order. Well, and notice this is an identity matrix. So, which means the numbers on the principal diagonal of this subset will remain, and they will be added together. So 1 times 1, 2 times 0 is going to cancel out, 3 times 0 is going to cancel out, 1 times 1. Add these together, you get 2. Then we take 1 stride to the right. So we are looking at the picture, so to speak, by taking a stride. We are scanning the picture. And the numbers the numbers you would pick in the weights depend on how you want to look at the picture. Because for a model to look at a picture, or is to look at vertical lines or horizontal lines or diagonal lines. So if you look, so that's why we have multiple filters, because we want to look at the picture from different, let's say, angles, and then add up everything we see, everything the model sees. Same thing here. 2 times 1, that's 2. 2 times 1 is 2. 4 times 1 is 4. So 4 plus 2 is 6. There's zeros. Eliminate 2 and 1. I think you get the idea, right? And of course, we can then take this and do this for to a tensor, which is a stack of matrices. Okay, that's all a convolution is.